Hi everyone, this is Spectre P, and we are Spectre AI. Quantum security is often presented as a solved problem, a story where mathematics replaces trust and proofs replace uncertainty. In theory, quantum mechanics gives us perfect secrecy. Any attempt to observe a key disturbs it, and that disturbance can be detected. But there is a gap between that promise and reality. Real systems are built from imperfect hardware, operate in noisy environments, and interact with adversaries who don't follow the assumptions that proofs rely on. In this video, we're going to take quantum security from first principles all the way to real-world failure. Not to dismiss the theory, but to understand where it breaks down in practice. We'll look at what security proofs actually guarantee, what they assume about attackers, and why systems that are mathematically secure can still fail once they're deployed. By the end, you'll understand not just how quantum security is supposed to work, but why real adversaries are able to exploit the space between theory and implementation, and why securing quantum systems is ultimately a systems problem, not just a mathematical one. So what does provably secure actually mean? In the language of quantum cryptography, it means that under a specific set of assumptions, ideal devices, perfect sources, perfect detectors, and well-defined threat models, the mathematics guarantees secrecy. And within that idealized world, those proofs are correct. But real systems don't live there. Real quantum networks are built from hardware, operated in noisy environments, and deployed against adversaries who don't respect the assumptions that make the proofs work. What we're really looking at here is a gap between quantum theory and real-world systems. A gap where perfect secrecy is proven on paper, but security has to survive in practice. And understanding that gap is the key to understanding why quantum security can fail outside the lab. This is the core mismatch. Most security proofs assume an adversary that is static, memoryless, and non-adaptive, executing a single isolated strategy against a single run of the system. That attacker doesn't learn, doesn't observe long-term behavior, and doesn't change over time. But the adversary that shows up in the real world looks nothing like that. Real attackers are adaptive, stateful, and patient. They operate across repeated interactions, observe how systems respond, and continuously update their strategy based on feedback. One model exists at a point in time. The other exists across time. And once an adversary can learn, the assumptions that make static security proofs work no longer hold. Security proofs are designed to bound behavior at a single point in time. They tell us that under fixed assumptions, a single execution of the protocol behaves safely, but real adversaries don't operate at a point in time. They operate across time. So each interaction, taken alone, looks harmless. Each run stays within acceptable bounds. But information accumulates. Patterns emerge. Correlations form. What is independent in theory becomes connected in practice. Learning doesn't happen in one execution. It happens across many. And once information can accumulate over repeated interactions, the assumptions that make static security proofs work quietly break down. Security metrics are often treated as neutral measurements, but they aren't. Error rates, thresholds, and alerts don't just observe system behavior. They shape it. When nothing changes, that silence conveys information. Stable metrics signal where the system tolerates variation and where it reacts. Over repeated interactions, attackers learn to read that stability, inferring safe operating regions without ever triggering an alarm. In practice, the system doesn't just monitor activity, it teaches adversaries how to remain invisible. At this point, the attacker is no longer just observing the system. They are optimizing against it. Adaptive adversaries don't try to cross detection thresholds because crossing the line is noisy, visible, and short-lived. Instead, they learn where the line is and shape their behavior to stay just below it. Each interaction is tuned to maximize information leakage while minimizing observable deviation. Speed is traded for stealth, and progress is measured over time rather than in a single event. What emerges is a smooth, controlled behavior that never looks anomalous, never triggers alarms, and never appears broken. From the defender's perspective, everything remains stable. From the attacker's perspective, stability is the goal. This is why so many real-world compromises persist for months or years without detection. The objective is not disruption or immediate failure, it's long-term access. And in that regime, persistence consistently beats detection. When defenders respond to adaptive attacks, the system doesn't reset. It evolves. Patches, threshold adjustments, and configuration changes are intentional defensive actions, but they are also observable events. Each change alters system behavior, shifts boundaries, and signals which controls actually mattered. Adaptive adversaries watch these changes closely. Stability after a fix confirms safe operating regions, while new reactions reveal fresh constraints. Over time, attackers don't just survive defensive responses, they learn from them. What begins as a corrective action becomes a new source of information, feeding the adversary's model of the system. The result is not an end to the attack, but a refinement of strategy. Each defensive update closes one door and quietly illuminates another. In this cycle, security isn't broken by a single failure. It's reshaped through continuous interaction. Under adaptive pressure, security stops being something you prove once and becomes something you sustain over time. Adversaries learn continuously, systems respond continuously, and validation never truly ends. There is no final configuration, no permanent threshold, and no static guarantee that holds indefinitely in a real environment. What matters is not whether a system passed a test or satisfied a proof at a single moment, but how it behaves, adapts, and is measured across time. Security emerges from ongoing interaction between systems and adversaries, shaped by feedback, constraints, and learning on both sides. In that reality, resilience is not a feature you deploy. It's a process you maintain. Security is not a state you reach and lock in. It's something you actively sustain, under constant pressure, over time. What this means in practice is that quantum security isn't a special case. It's an example of a much broader systems problem. The moment a system is deployed, it becomes part of an environment shaped by people, processes, incentives, and adversaries who adapt over time. Proofs, metrics, and controls still matter, but they no longer stand alone. They operate inside living systems that evolve under pressure. Security, in this context, is not about reaching a final configuration or declaring a system safe. It's about continuously observing how the system behaves, how it responds to change, and how those responses shape adversary behavior. This way of thinking applies far beyond quantum networks, to any system where learning adversaries interact with real infrastructure. Once you see security this way, the question stops being, is this system secure? And becomes, how does this system behave over time under adaptive pressure? At the end of the day, security is not something you arrive at and declare finished. It isn't a box you check, a proof you cite, or a configuration you lock in and walk away from. The moment a system is deployed, it enters a world shaped by time, change, and adversaries who learn. Every interaction adds context. Every response creates feedback, and every period of stability carries information. Security, in this reality, is not defined by a moment of correctness, but by how a system behaves over its lifetime. It's measured in adaptation, in observation, and in continuous validation under pressure. There is no final state where the problem is solved once and for all. There is only an ongoing process of understanding, adjusting, and sustaining resilience. Security is not a destination. It's a process. Before we talk about attacks, protocols, or failure modes, we need to be clear about what quantum security is actually trying to protect. At its core, the goal is not hardware, devices, or even algorithms. It's information. Specifically, it's the secrecy of information as it moves from one party to another through an uncertain and noisy physical world. Quantum security was designed to protect information at the moment it is created and shared, before any assumptions about trust, infrastructure, or computation are applied. This is why quantum systems focus so heavily on measurement, disturbance, and uncertainty, because information itself is the asset and leakage is the failure. Everything that follows, from protocols to proofs to countermeasures, exists to preserve that single objective. And if we lose sight of what is being protected at the most fundamental level, it becomes impossible to understand why real systems fail once they leave the lab. If information is the asset, then the first threats to security don't come from attackers. They come from reality itself. Information doesn't travel through a perfect world. It moves through noisy channels, lossy systems, imprecise devices, and environments filled with uncertainty. Signals fade, measurements fluctuate, and interactions introduce disturbance even when no one is trying to interfere. These effects are not malicious. They are physical. But they matter, because every imperfection creates the possibility of leakage. Quantum security begins here, not with adversaries, but with the recognition that information is fragile by default. Before we ever talk about attacks or exploitation, we have to understand the natural pressures that act on information as it moves through real systems. Because once information is exposed to noise, loss, and uncertainty, the boundary between protection and compromise becomes much thinner than it appears. This is where classical intuition starts to fail. In the classical world, information feels solid and well-behaved. Bits can be copied perfectly, observed without consequence, and measured without changing the system that produced them. That intuition works because classical information is detached from the physical process that carries it. But quantum information doesn't behave that way. In quantum systems, information is inseparable from the physical state of the system itself. Observation is not passive. Measurement changes what is being measured. States overlap, outcomes are probabilistic, and attempting to extract information inevitably introduces disturbance. This is not a flaw in the system. It's a fundamental property of how quantum information exists, and it's precisely this breakdown of classical intuition that makes quantum security possible, and at the same time, makes it far more subtle than it first appears. To understand both the promise and the failure modes of quantum security, we have to let go of the idea that information can be observed without consequence. This is the fundamental rule that everything else in quantum security rests on. Measurement changes the system. In quantum mechanics, observation is not passive. Extracting information is a physical interaction that alters the state being observed. Before measurement, a quantum system exists in a fragile, probabilistic state defined by uncertainty. The act of measurement forces that state to change, collapsing possibilities, introducing disturbance, and leaving a trace of interaction behind. This is not a limitation of technology or an implementation flaw. It is a property of nature itself. Quantum security relies on this rule because it means information cannot be extracted quietly. But it also means that real systems must constantly manage a trade-off between learning and disturbance. Every bit of information gained has a cost, and that cost shows up as measurable change. Understanding this principle is essential because everything that follows — protocols, thresholds, detection strategies, and even attacks — is built on how systems navigate this unavoidable interaction between observation and disturbance. Once measurement is understood as a physical interaction, the next consequence becomes unavoidable. Information and disturbance are inseparable. Gaining more information about a quantum system always introduces more disturbance into that system, There is no operating point where information can be extracted freely and invisibly. Instead, security exists along a continuous trade-off. At one extreme, very little information is gained and disturbance is minimal. The system remains stable, but there is little to exploit. At the other extreme, large amounts of information are extracted, but the resulting disturbance is obvious and quickly detected. Real quantum systems operate in the narrow region between these extremes, where some noise is tolerated and some information can be exchanged. This is where security actually lives. Thresholds, error rates, and detection limits exist precisely because this balance cannot be eliminated. It can only be managed. Understanding this trade-off is essential because it defines both how systems defend themselves and how adversaries decide where and how to operate. At this point, it's natural to ask why quantum systems tolerate any errors at all. If disturbance reveals information leakage, why not demand perfect behavior? The answer is that real systems cannot operate under zero tolerance. Noise is unavoidable. It comes from the environment, the hardware, the channel, and the physics of measurement itself. Even in the absence of any adversary, signals fluctuate, components drift, and outcomes vary. If a system treated every deviation as a failure, it would never function. Security, therefore, does not mean eliminating noise. It means operating within an acceptable range of it. Thresholds and tolerance bands exist because they must. They are what allows secure communication to continue in an imperfect world. But once tolerance becomes necessary for operation, it also becomes a space that can be exploited. Understanding why errors are allowed is essential, because it explains both how quantum security works and where its most subtle vulnerabilities begin. Once tolerance becomes necessary for a system to function, it also becomes a place to hide. Not all behavior that falls within acceptable bounds is benign. Natural noise is unstructured and random, but adaptive adversaries introduce behavior that is deliberate, repeatable, and optimized, while still remaining inside the tolerance band. From the system's perspective, nothing looks wrong. Metrics stay within range, alerts remain silent, and operation continues as expected. But from the attacker's perspective, tolerance provides cover. By shaping signals carefully and operating just below detection thresholds, adversaries can embed intentional behavior inside what the system is designed to allow. This is why real-world attacks don't announce themselves with spikes or failures. They blend into normal operation. The system is not misconfigured. It is functioning exactly as designed. And that design choice is what makes subtle exploitation possible. This is where learning turns into control. Adaptive adversaries don't rely on brute force or random probing. They explore a space of possible behaviors and systematically eliminate what fails. Early on, many strategies are tested. Some trigger responses, some introduce too much disturbance, and others simply don't produce useful information. Those paths are discarded. What remains is a narrowing set of behaviors that are quiet, effective, and repeatable. Over time, the attacker's strategy space collapses from many possibilities to a small number of carefully chosen actions that consistently stay within acceptable bounds. This process doesn't require breaking the system or exceeding thresholds. It relies on feedback, repetition, and patience. What looks like normal operation from the outside is, in reality, the result of deliberate optimization. The attack is no longer exploratory, it's intentional, refined, and sustained. Once adversaries understand how systems tolerate noise and respond to disturbance, they can translate learning into very specific techniques. This is where abstract behavior becomes concrete. In time-shift attacks, for example, attackers don't change the content of a signal. They change when it arrives, exploiting subtle differences in detector efficiency across time. In detector bias and efficiency mismatch attacks, adversaries shape signals so that one detector is more likely to respond than another, while overall error rates remain within tolerance. In chained attack scenarios, these techniques aren't used in isolation. Small amounts of information are extracted across many interactions, combined with the feedback from system responses and refined over time. None of these actions look abnormal on their own. Metrics stay stable. Thresholds are respected. The system continues to operate as designed, but collectively, these behaviors allow attackers to influence outcomes and extract information without ever triggering alarms. What matters here is not the individual technique, but the pattern. Learning, adaptation, and control, operating quietly inside the space the system must allow. From the defender's perspective, security events appear local and independent. Small deviations are observed, classified, and resolved one at a time. Noise looks like noise. Drift looks like drift. Each response is reasonable in isolation, and nothing ever appears severe enough to demand intervention. But attackers don't experience the system that way. They operate across time, accumulating information from many small interactions that defenders treat as unrelated. What looks like a series of harmless events from above becomes a coherent structure when viewed cumulatively. Each response, each tolerance, each moment of stability contributes another piece of the picture. Defenses react locally, but attacks compound globally. And once adversaries are able to chain these small effects together, the system can remain operational, compliant, and apparently secure, even as meaningful information leakage accumulates beneath the surface. This is why chaining fundamentally changes the game. It exploits the difference between how defenders observe systems and how attackers learn from them. This is where detection-based security models begin to fall behind. Defenders operate in a reactive loop. Observe an event, analyze it, respond, and then reset. Each decision is local, bounded in time, and evaluated independently. That approach makes sense when threats are isolated and short-lived. But adaptive adversaries don't operate in loops. They operate along a continuous timeline. They learn across interactions, accumulate information without resetting, and refine their behavior with every response the system provides. While defenses repeatedly start over, attackers never do. This creates an asymmetry that detection alone cannot resolve. Even perfect detection logic reacts after the fact, while learning happens before, during, and across those reactions. Over time, the gap between reactive defense and cumulative learning widens. And once that gap exists, improving detection speed or accuracy doesn't close it. It simply feeds the adversary more information. This is why detection and response models struggle against adaptive threats. The timelines don't match, and the attacker's advantage grows with every cycle. Up to this point, we've been treating security as something that can be evaluated one event at a time. A system is checked, a metric is measured, and the result is classified as normal or abnormal. That model assumes that each event is independent, and that security can be decided in discrete snapshots. But adaptive adversaries don't operate in snapshots. They operate along trajectories. What matters is not whether any single event passed a threshold, but how behavior evolves over time. Small deviations that look harmless in isolation can form meaningful patterns when viewed cumulatively. Learning, correlation, and direction are invisible to point-in-time checks. This is why detection-based models struggle. They repeatedly reset their understanding, while attackers never reset what they've learned. Once learning enters the picture, security cannot be evaluated as a series of isolated passes or failures. It has to be evaluated as behavior unfolding over time. If we measure the wrong thing, events instead of trajectories, we end up declaring systems secure precisely when they are quietly drifting in the wrong direction. Once security is understood as something that unfolds over time, the way it's evaluated has to change as well. Instead of treating security as a sequence of isolated checks, continuous validation looks at how systems behave across extended operation. Baselines are established, not as fixed targets, but as evolving references. Correlations between signals matter more than individual readings. Slow drift, subtle coupling, and directional change become visible only when behavior is observed longitudinally. This model doesn't wait for a single event to cross a threshold before reacting. It continuously assesses whether the system's trajectory still aligns with expected behavior. In doing so, it mirrors how adaptive adversaries actually operate. Across time, without resetting, continuous validation doesn't promise perfect security, but it restores symmetry between defenders and attackers by measuring what truly matters: how systems evolve under sustained interaction. At this point, it's important to be clear about what continuous validation is not. It is not a more sensitive alerting system, and it is not a faster response loop. It does not rely on signatures, predefined rules, or static thresholds to decide whether a system is secure. Those approaches all treat security as a series of discrete events, something that either triggers or doesn't. Continuous validation takes a fundamentally different view. It is not concerned with whether a single event looks abnormal, but with how behavior evolves over time. Alerts, thresholds, and signatures can still exist, but they are no longer the foundation of security decisions. What matters instead is continuity, correlation, and direction. The goal is not to react to individual incidents, but to understand whether the system's trajectory remains consistent with expected behavior. Without this distinction, continuous validation gets mistaken for better monitoring. In reality, it represents a shift away from event-based thinking toward measuring security as a living, evolving process. If security is going to be evaluated continuously rather than one event at a time, it requires a very different foundation than traditional detection systems. First, it requires longitudinal memory. Systems must remember past behavior because learning adversaries never reset what they've observed. Security decisions cannot be made in isolation if history matters. Second, it requires behavioral baselines that evolve over time. Normal is not a fixed value or a static threshold. It drifts as systems, environments, and usage patterns change, and it must be tracked as a trend rather than a point. Third, continuous validation depends on cross-signal correlation. Individual metrics rarely carry meaning on their own. Insight emerges from the relationships between multiple signals observed together. And finally, it requires trajectory awareness. Direction matters more than momentary deviation. Slow, consistent drift can be far more dangerous than a sudden spike. Taken together, these requirements define a security model that no longer reacts to isolated events, but measures how systems behave over time. This is what continuous validation actually demands. In most real-world systems, the data needed for continuous validation already exists, but it isn't integrated over time. Logs capture individual events, metrics summarize system states, alerts flag specific conditions, and storage retains historical records. Each component works as designed, and each serves a legitimate purpose. The problem is not the absence of data, but the way it is organized. These signals live in separate systems, owned by different tools, teams, and workflows. They are evaluated independently, often in response to incidents, rather than continuously as a unified behavioral record. As a result, systems lose memory. Patterns that only emerge over time are fragmented across silos, and long-term trajectories are never fully reconstructed. Security decisions remain local and reactive, even though adversaries operate globally and cumulatively. This disconnect is why continuous validation is difficult in practice, not because the ideas are unclear, but because most architectures were never designed to preserve continuity across time. If continuous validation is the goal, then something fundamental has to change in how security systems are designed. In most environments today, the necessary data already exists. Logs capture events, metrics summarize system state, alerts flag conditions, and storage retains history. But these elements live in separate systems, owned by different tools and teams, evaluated independently, and often discarded after short windows. As a result, security loses memory. Patterns that only emerge across time are fragmented, and behavior is never fully reconstructed. What must change is not the addition of more signals, but the preservation of continuity. Security systems must maintain shared memory across time, allowing behavioral baselines to evolve, signals to be correlated, and trajectories to be understood as a whole. When memory is preserved, the past informs the present, and validation becomes possible. Without that continuity, even the best tools operate in isolation. This is why security must be designed as a continuous system, not assembled from disconnected components. Continuity is what enables validation. What continuous validation enables is early visibility into adaptive behavior, before any thresholds are crossed. Instead of waiting for a system to violate a predefined limit, continuous validation observes how behavior evolves across time. Individual signals that look insignificant on their own begin to matter when viewed together, as patterns, correlations, and direction slowly emerge. What's important here is not the size of any single deviation, but the shape that forms as those deviations accumulate. Direction matters more than magnitude. Trajectory matters more than momentary noise. Long before a traditional security system would react, subtle drift and structured change become visible to a model that preserves memory and context. This doesn't eliminate uncertainty and it doesn't predict the future, but it shifts security from reacting after damage occurs to recognizing risk while there is still time to respond. By measuring behavior continuously rather than episodically, defenders regain symmetry with adaptive adversaries, not by triggering alarms sooner, but by seeing change earlier. Even with continuous validation, it's important to be clear about what security can and cannot do. Continuous validation does not eliminate uncertainty. It does not provide perfect visibility into intent, and it does not guarantee absolute security. Adaptive systems operate in probabilistic environments, shaped by noise, complexity, and incomplete information. What continuous validation changes is not the existence of uncertainty, but how that uncertainty is managed. Instead of pretending that systems can be made perfectly secure, it acknowledges that risk is always present and must be evaluated continuously. Prediction remains limited, intent remains partially hidden, and guarantees remain conditional. Security, even under the best models, is never binary. It is a matter of likelihood, confidence, and trade-offs over time. By recognizing these limits explicitly, continuous validation avoids false certainty and overconfidence. It doesn't promise perfection. It provides a more honest, defensible way to reason about security in a world where uncertainty cannot be removed. At this point, it becomes clear that security is not about eliminating risk entirely. It's about managing it responsibly. In real systems, uncertainty is unavoidable. Information is incomplete. Environments change, and adversaries adapt. Every security decision is made with partial visibility and imperfect data. The goal is not to pretend that risk can be driven to zero, but to understand where it exists, how it evolves, and which risks matter most over time. Effective security requires judgment, deciding when to intervene, when to tolerate deviation, and when to accept residual exposure in exchange for functionality and performance. This is why security is ultimately a discipline of risk management rather than risk elimination. By acknowledging uncertainty instead of denying it, systems can be designed to respond proportionally, adapt intelligently, and remain resilient over time. Security succeeds not by promising certainty, but by making informed decisions under uncertainty. At first glance, perfect security sounds like the ideal objective. If every vulnerability is eliminated and every deviation is prevented, then nothing can go wrong. But in real systems, optimization without margin creates fragility. When a system is tuned too tightly, it loses the ability to absorb uncertainty, adapt to change, or respond gracefully to unexpected conditions. Small stresses that would otherwise be harmless begin to propagate, and failure modes become sharper rather than rarer. Security designed for perfection leaves no room for learning, no buffer for noise, and no flexibility under pressure. Instead of becoming stronger, the system becomes brittle. Real security requires slack, not as a weakness, but as a source of resilience. Slack allows systems to tolerate variation, adapt to evolving conditions, and recover without cascading failure. In practice, the pursuit of perfect security often produces systems that fail faster and more catastrophically. That's why effective security is not about eliminating every risk, but about designing systems that can survive, adapt, and respond under uncertainty. When we talk about risk in security systems, not all risk is created equal. Acceptable risk is visible, bounded, and actively managed. It exists within known limits, is acknowledged explicitly, and is monitored over time. This kind of risk is not ignored. It's understood. Decisions are made with awareness of where the boundaries are and what trade-offs are being accepted. Hidden risk, by contrast, is implicit and accumulating. It does not trigger alerts, does not violate thresholds, and often remains unseen precisely because it looks normal in isolation. Over time, these small, unmeasured exposures can compound into something far more dangerous than the risks we knowingly tolerate. This is why hidden risk is the more dangerous risk. Systems that chase the illusion of perfect security often drive risk underground, where it can grow without visibility or control. Effective security does not attempt to eliminate all risk. It prioritizes making risk explicit, measurable, and bounded, so it can be managed deliberately rather than discovered too late. Every real security decision exists at the intersection of cost, performance, and security. These three factors are inseparable. Improving one inevitably constrains the others. Increasing security often comes at the expense of performance, adding latency, overhead, or operational complexity. Improving performance can reduce the margin available for validation, monitoring, or redundancy, and reducing cost limits how much resilience, diversity, or continuous oversight a system can support. This is not a failure of engineering or planning. It is an unavoidable reality of operating complex systems. What matters is not eliminating trade-offs, but making them explicit. When trade-offs are acknowledged, decisions can be made deliberately with a clear understanding of what is being gained and what is being sacrificed. When trade-offs are ignored, risk doesn't disappear. It becomes hidden. Effective security is not about maximizing one corner of this triangle, but about choosing a balance that aligns with real-world constraints, operational goals, and acceptable risk over time. Even when systems are carefully designed, well-monitored, and responsibly managed, some level of risk always remains. This is what we call residual risk. It is not the result of negligence or failure, but a consequence of operating in an uncertain world. Complexity, noise, incomplete information, and evolving conditions ensure that no system can ever achieve absolute certainty. The goal of security, therefore, is not to eliminate uncertainty, but to manage it deliberately. Residual risk must be acknowledged, measured, and accepted as a part of responsible operation. When teams deny its existence, they tend to drive risk underground, where it becomes harder to see and more dangerous over time. When residual risk is recognized openly, it can be bounded, prioritized, and revisited as conditions change. This is why mature security programs focus less on the promise of total protection and more on sustained oversight. Security succeeds not by pretending uncertainty can be removed, but by managing what remains with clarity, discipline, and intent. Once we accept that residual risk is unavoidable, the real question becomes how to decide which risks actually matter. Not all risks deserve the same level of attention. Some have low impact, some are unlikely to materialize, and others may exist for long periods without changing in meaningful ways. Effective prioritization requires context. Impact matters. How severe the consequences would be if a risk materialized. Likelihood matters. How plausible it is given current conditions. But just as important is trajectory. Risks that are growing, drifting, or accumulating over time often deserve more attention than risks that are static, even if their current impact appears small. This is why security decisions cannot be made from a checklist or a score alone. They require judgment informed by how systems evolve under real conditions. By evaluating risk as a landscape rather than a single point, defenders can focus resources where they matter most, addressing emerging threats early while avoiding unnecessary intervention where stability exists. Prioritization, not elimination, is how security decisions stay grounded in reality. Deciding when to intervene is one of the most difficult judgment calls in security. Intervening too early can waste resources, introduce instability, and create unnecessary friction in systems that may have corrected themselves naturally. Intervening too late, on the other hand, allows risk to compound, making recovery more costly and damage harder to contain. This is why effective security doesn't rely on rigid triggers or single alerts. Instead, it operates within a decision zone, a region where uncertainty exists and judgment matters. As behavior evolves over time, signals gradually become clearer, and the cost of inaction begins to outweigh the cost of response. The goal is not to wait for absolute certainty, because that moment rarely arrives, nor is it to react at the first sign of deviation. The intervention point is chosen deliberately, based on trajectory, context, and accumulated evidence. This is why timing matters more than detection. Security succeeds not by responding faster, but by intervening at the right moment, when action can still change the outcome without destabilizing the system. Not every deviation is a signal, and not every change requires intervention. In real systems, some variation is natural, expected, and self-limiting. Noise fluctuates, processes oscillate, and conditions drift within healthy bounds without any corrective action. When defenders intervene too aggressively, they can destabilize systems that would otherwise settle on their own. This is why knowing when not to intervene is just as important as knowing when to act. Disciplined security recognizes the difference between meaningful trajectory change and ordinary variation. It resists the impulse to react to every fluctuation, understanding that excessive intervention creates churn, introduces new failure modes, and generates unnecessary feedback. In many cases, restraint preserves stability better than action. By allowing systems to absorb minor deviations without interference, defenders avoid overfitting responses to transient conditions. This is not inaction. It is deliberate judgment. Security improves not by constant reaction, but by intervening only when accumulated evidence indicates that risk is growing rather than resolving itself. One of the most important realities in adaptive security is that defensive actions themselves become information. Every intervention changes the system's behavior, and those changes are observable. When defenders respond to perceived risk, they don't just alter outcomes. They create feedback that adversaries can learn from. An intervention reveals where boundaries exist, which behaviors triggered a response, and which ones did not. Over time, this feedback loop allows adversaries to refine their approach, adjusting tactics to remain below detection while still accumulating advantage. This is why security decisions cannot be viewed as isolated reactions. Each response becomes part of the signal, shaping future behavior on both sides. Adaptive adversaries are not just reacting to systems, they are reacting to defenders. Understanding this feedback loop is critical. It explains why repeated intervention without reflection can actually accelerate adversary learning and why restraint, timing, and context matter. In a dynamic environment, every decision contributes to the evolving system, and security outcomes emerge from that continuous interaction. At the end of the day, security is not about reacting perfectly to every threat. It's about enduring pressure over time. Risk management acknowledges that uncertainty cannot be eliminated, trade-offs cannot be avoided, and decisions will always be made with incomplete information. Resilience is what allows systems to operate effectively despite those realities. A resilient system is not one that never experiences stress, but one that absorbs stress without losing control. It bends without breaking, adapts without destabilizing, and continues functioning even as conditions change. This is why security cannot be measured solely by how quickly systems react, but by how well they hold together under sustained pressure. Resilience shifts the focus from momentary responses to long-term survivability. Instead of chasing every deviation, it prioritizes stability, recovery, and continuity. Security succeeds not when systems appear flawless in the moment, but when they remain dependable across time. This is the transition from managing individual risks to designing systems that can endure. Security resilience is not about preventing every failure. It is about enduring pressure over time. A resilient system assumes that stress will accumulate, that components will degrade, and that some defenses will fail. What matters is not whether failure occurs, but how the system behaves when it does. Resilience means reduced function, not collapse. The system may operate at lower performance with fewer guarantees or under tighter constraints, but it continues to deliver value. Most importantly, resilience preserves continuity for users. From the outside, the system remains usable, predictable, and trustworthy, even as internal conditions change. In this sense, security is not a moment in time. It is a process, measured by how long meaningful operation can be sustained under pressure, not by whether defenses ever fail. Detection and resilience are often treated as the same thing, but they serve fundamentally different purposes. Detection focuses on awareness. It tells you that something has happened or is happening somewhere in the system. Alerts fire, dashboards update, signals spike. But detection alone does not determine what happens next. Resilience focuses on outcome. It determines whether the system continues to function when stress accumulates, when failures occur, and when conditions deviate from expectations. A resilient system does not depend on perfect visibility. It assumes that some events will be missed, some alerts will arrive late, and some failures will go unobserved. What matters is that the core structure holds. Function may be reduced, performance may degrade, but the system continues to deliver value. Detection creates information. Resilience creates survival. In practice, systems that rely only on detection react loudly but fail quietly, while systems designed for resilience remain stable even when awareness is incomplete. This is why detection can support security, but resilience ultimately defines it. Designing for adaptive adversaries means accepting that the opponent does not remain fixed. An adaptive adversary observes the system, experiments with it, and refines its behavior over time based on the system's own responses. Each interaction becomes data. Each defensive adjustment becomes a signal. Over repeated cycles, the adversary learns which actions produce results and which do not. In this environment, static defenses degrade even if they were initially effective, because the threat model itself is being updated continuously. Resilient systems account for this by assuming that probing will occur, that behaviors will change, and that pressure will increase gradually rather than arriving all at once. The goal is not to outsmart the adversary in a single moment, but to prevent learning from converging toward control. Designing for adaptive adversaries therefore requires structures that remain stable under repeated interaction, limit what can be inferred from system responses, and preserve function even as external strategies evolve. Security in this context is not about blocking a specific attack, but about sustaining control in the presence of an opponent that learns. Redundancy is often assumed to improve security, but redundancy only works when failures are independent. When multiple defenses share the same structure, the same assumptions, or the same underlying logic, they tend to fail together. This creates the illusion of robustness while preserving a single mode of collapse. True resilience requires redundancy without correlation. Each component may serve a similar role, but it must fail differently, respond differently, and expose different weaknesses under pressure. In a resilient design, stress does not propagate cleanly from one element to the next. A disturbance that degrades one component does not automatically compromise the others. This breaks the adversary's ability to generalize learning, because information gained from probing one path does not translate reliably to the rest of the system. Correlated systems leak structure. Uncorrelated systems contain it. The goal is not to prevent failure entirely, but to ensure that failure remains localized, partial, and non-inferential. In this way, redundancy becomes a tool for endurance rather than a multiplier of hidden risk. Diversity as a defensive strategy works because it prevents learning from transferring. A single probing action enters the system, but instead of encountering a uniform response, it is diffused, absorbed, reflected, bent, and fragmented in different ways across the environment. Each interaction reveals a different behavior, governed by different internal rules, so information gained in one region does not apply to the next. This breaks the attacker's ability to generalize. A probe that learns how to pass through one mechanism gains no advantage elsewhere, because the system refuses to repeat itself. Over time, diversity increases the cost of adaptation by forcing continuous relearning rather than allowing convergence toward an optimized strategy. The goal is not to stop probing entirely, but to ensure that probing never becomes efficient. In this way, diversity transforms exposure into friction. Instead of a single path to exploitation, the adversary faces a landscape of incompatible responses, where progress in one direction produces no leverage in another. Security emerges not from strength alone, but from the deliberate refusal to behave consistently. Time becomes a defensive dimension when systems stop trying to block attacks immediately and instead control how long those attacks remain viable. A probe enters the system with a clear objective and a synchronized plan, but almost immediately its progress is delayed. As time stretches, the probe is desynchronized, split into components that no longer align or arrive together. Portions of the action stall, frozen in intermediate states where forward progress becomes uncertain. Other fragments simply expire, fading out before they can contribute to a successful outcome. What remains is reordered, arriving late, out of sequence, and stripped of the assumptions that made the original strategy effective. Nothing here looks dramatic, but the effect is decisive. Attacks that depend on timing, coordination, or rapid iteration lose coherence as time works against them. By the time the probe reaches its destination, the conditions it relied on no longer exist. In this way, time does not act as a barrier, but as friction, quietly increasing cost, breaking synchronization, and turning persistence into exhaustion rather than success. Containment over prevention means accepting that failure will occur, and designing systems so that failure does not matter. In this view, security is not about stopping every incident at the boundary, but about ensuring that when something breaks, the damage remains confined. The failure is real, visible, and contained within a defined region, while the rest of the system continues to operate normally. Boundaries are not there to keep all threats out. They exist to prevent localized problems from becoming global ones. By isolating failure, limiting its scope, and sealing off its effects, the system preserves continuity without requiring perfect detection or immediate response. Recovery can happen in place without cascading resets or widespread disruption. This approach treats failure as an expected condition rather than an exception, and resilience emerges not from avoiding breakdowns, but from ensuring that breakdowns never escape their containment. Monitoring the system, not the attacker, means shifting attention away from external threats and toward internal behavior. Instead of trying to predict who is probing or why, the system continuously observes its own vital signs, temperature, flow, load, error rate, and latency, and watches for deviation from normal operation. These signals are stable, measurable, and meaningful regardless of the source of disruption. When something begins to change internally, it indicates that the system's behavior has shifted, even if the cause remains unknown. This approach avoids chasing adversaries and focuses on maintaining coherence, balance, and performance within the system itself. By tracking internal state rather than external intent, defenders gain early visibility into stress, degradation, and loss of control without relying on attribution or perfect detection. Security, in this model, emerges from self-awareness, knowing when the system is healthy, when it is drifting, and when intervention is required, independent of who or what triggered the change. Humans in the control loop means recognizing the limits of automation and the value of judgment. Automated systems are excellent at monitoring internal behavior, tracking metrics, and detecting subtle changes over time. They observe temperature, flow, load, error rate, and latency continuously, without fatigue or distraction. But automation does not decide what matters. That responsibility remains with the human. In this model, the system presents stable, interpretable signals, while the human evaluates context, intent, and consequence. Intervention is not automatic, nor is it constant. Sometimes the correct decision is to act, and sometimes the correct decision is to wait. By keeping humans in the loop, the system avoids brittle reactions to noise and preserves flexibility in the face of uncertainty. Automation maintains awareness, while humans apply judgment, experience, and restraint. Security emerges not from removing people from the process, but from placing them exactly where decisions must be made, when change is real, meaningful, and worth responding to. Up to this point, everything we've discussed has been about systems, how security behaves over time, how resilience emerges from structure, restraint, and judgment, and how failure can be managed rather than feared. None of those principles change when we move into quantum systems. What changes is the environment in which those principles must operate. In quantum security, margins are thinner, tolerances are tighter, and small deviations carry disproportionate consequences. Timing, noise, loss, and physical implementation details become inseparable from security itself. The same system-level ideas still apply, but the slack disappears. Where classical systems can absorb imprecision, quantum systems amplify it. This transition marks the point where abstract resilience principles meet physical reality, and where design choices move from being forgiving to being decisive. From here forward, we're no longer talking about security in general. We're talking about what those ideas mean when the underlying system is governed by quantum constraints. Quantum security is especially exposed because the margin for error is vanishingly small. In these systems, operation occurs within tight constraints, where acceptable behavior is bounded by narrow tolerances rather than broad safety margins. Small fluctuations that would be harmless in classical systems, minor noise, timing jitter, loss, or drift, can be amplified into meaningful security consequences. The system may still be operating correctly, but only just, and even slight deviations push it closer to failure. This exposure is not the result of poor design or weak theory, it is a consequence of physics itself. Quantum systems cannot absorb imprecision the way classical systems can. Instead, they make deviations visible and consequential. Security, therefore, becomes inseparable from control, calibration, and continuous stability. In this environment, resilience is not about dramatic attacks or catastrophic breaks, but about staying inside a very narrow operating window where correctness, trust, and security all overlap. Quantum key distribution is often described as a protocol, but in practice it operates as a system. At the center is an idealized exchange between parties, governed by clean mathematical rules and strong theoretical guarantees. That protocol is correct, elegant, and well understood, but it exists inside a much larger physical reality. Around it are detectors, optical fibers, timing systems, control electronics, calibration routines, and environmental influences that the protocol itself does not model. These surrounding elements dominate the system's behavior because they determine how the protocol is actually implemented. Loss, noise, drift, thresholds, and hardware imperfections all shape what security looks like in practice. Even when the protocol is flawless, the system that carries it can behave in ways the theory never anticipated. This is not a flaw in quantum cryptography. It is a reminder that security does not emerge from abstract rules alone. In quantum systems especially, security is a property of the entire physical implementation, and understanding that distinction is essential before asking what proofs can and cannot guarantee. Proofs still matter, because they tell us what security looks like under clearly defined assumptions. Inside this bounded region, behavior is predictable, guarantees are meaningful, and the mathematics is sound. Provable security gives us confidence that if the system behaves exactly as modeled, certain outcomes are impossible. But those guarantees exist within a carefully defined envelope. Outside, it lies the physical implementation, where real devices, timing, noise, loss, calibration, and environmental factors introduce behavior the proofs do not capture. This does not invalidate the proofs, it limits their domain. The danger arises when results proven under idealized conditions are implicitly extended into regions they were never designed to describe. Understanding where proofs apply, and where they stop, is essential for building resilient quantum systems. Proofs provide certainty within their assumptions, but security in practice depends on recognizing the boundary between mathematical models and physical reality, and designing systems that respect both. Proofs stop helping at the point where their assumptions end. Within the domain they describe, mathematical guarantees are clear and powerful, but beyond that boundary, the proofs simply have nothing more to say. This does not mean the theory is wrong. It means the model no longer captures the behavior of the system. Outside the proof domain, physical effects dominate. Timing, drift, loss, noise, calibration errors, component aging, and environmental variation. These influences are not adversarial by nature, but they are unmodeled and therefore invisible to the proof. As systems move deeper into real-world operation, security becomes governed less by what can be proven and more by what can be observed, measured, and controlled. Understanding where proofs stop helping is essential because it marks the transition from theoretical certainty to practical responsibility. Beyond this point, security must be maintained not by guarantees alone, but by continuous validation and disciplined system design. Continuous validation is how security persists once proofs stop providing answers. Instead of relying on a single guarantee made at design time, the system repeatedly measures its own behavior during operation. Key parameters are observed continuously, not to catch an attacker, but to detect drift from expected performance. As conditions change, through noise, loss, aging components, or environmental variation, the system adapts, re-establishing stability without requiring perfect knowledge of the cause. This process forms a loop. Measure, detect drift, adapt, and repeat. There is no final state where validation can stop, because the system itself never stops changing. In quantum networks especially, where tolerances are narrow and deviations are amplified, continuous validation becomes the mechanism that replaces static assurance. Security is maintained not by proving that nothing can go wrong, but by ensuring that when behavior changes, it is seen, understood, and corrected in time. What quantum defenders should measure are not attacks, but the slow, persistent signals that reveal how the system is changing over time. Drift matters because it indicates gradual loss of alignment between expected and actual behavior. Bias matters because small consistent offsets can accumulate into meaningful security consequences. Loss matters because attenuation reshapes signal statistics and reduces margin. Timing matters because quantum systems are exquisitely sensitive to synchronization, and even slight skew can alter outcomes. Error rate matters not as an absolute value, but as a trend. How it evolves, stabilizes, or slowly worsens. These signals do not announce themselves dramatically, and they rarely cross clean thresholds. Instead, they emerge as patterns visible only through continuous observation. Effective quantum defense depends on watching these measures together, over time, and understanding how they interact. Security lives in these slow-moving indicators because they reveal loss of control long before any explicit failure occurs. Not every deviation requires intervention. In complex systems, especially quantum networks, natural variation is expected and often self-correcting. Small fluctuations, transient noise, and brief excursions within acceptable bounds are part of normal operation, not indicators of compromise. Overreacting to these signals can introduce instability, amplify noise, and reduce overall system resilience. Self-limiting behavior should be allowed to settle on its own, without forcing unnecessary corrections that disrupt equilibrium. Effective defense depends on distinguishing between meaningful change and benign variability, and on resisting the urge to act simply because something moved. By maintaining patience and observing trends rather than moments, defenders preserve stability and avoid turning normal system behavior into a source of risk. In this context, restraint is not inaction. It is a deliberate choice that protects the system from unnecessary interference. Loss of control is not detected by a single spike or a momentary threshold crossing. It appears when a system stops correcting itself. Within the expected range, normal variation and noise fluctuate but remain bounded, drifting back toward equilibrium over time. What matters is not magnitude, but persistence. When deviation continues in one direction, when correction no longer occurs, and when the system's behavior diverges steadily from its baseline, control has been lost. This shift is subtle and often quiet, but it is decisive. At this point, the system is no longer governed by its internal stabilizing mechanisms, and inaction becomes riskier than intervention. Detecting loss of control, therefore, requires watching behavior over time, not reacting to isolated events. The moment to act is not when something first changes, but when change becomes directional, sustained, and self-reinforcing. Security is an ongoing discipline because it unfolds over time, not in isolated moments. Effective defense begins with observation, continuously watching system behavior without assuming intent. Measurement follows, turning raw behavior into meaningful signals that reveal drift, bias, loss, and timing changes. Response is applied deliberately only when those signals indicate genuine loss of control rather than normal variation. Adaptation closes the loop, adjusting the system so stability is restored without overcorrection. This process does not terminate because the system itself never stops changing. There is no final secure state, only continuous assessment across time. Security emerges from maintaining this discipline, observing, measuring, responding, and adapting in sequence, rather than chasing individual threats or relying on static guarantees. In this model, resilience is not achieved once, it is practiced continuously. The core lesson across all of this is that security is not something you prove once and then move on from. It is a property of the entire system, not a guarantee provided by any single protocol or mathematical result. Static proofs may offer clarity under ideal assumptions, but they fail against adaptive, persistent behavior in the real world. True resilience comes from endurance over time, not from detection, alerts, or reactive control. Quantum systems make this reality unavoidable by amplifying small deviations and removing the margin for error that classical systems often rely on. When proofs end, continuous validation must take over, measuring the right signals, ignoring benign variation, and acting only when control is genuinely lost. In the end, security is not a destination or a state that can be reached and declared complete. It is a disciplined process, practiced continuously, as systems evolve, conditions change, and uncertainty persists over time. Thank you for watching. If you found this useful, please like the video and subscribe to the channel. It really helps us keep building deep, real-world quantum security content. You can visit spectreai.ai to explore over 55 hands-on quantum security labs and learn by doing, not just by theory. If you're interested in going deeper, you can also find our books on Amazon. And finally, leave a comment and let us know what you'd like to learn next. We read them all. Thanks again, and we'll see you in the next video.